which is quite a lot, so we'll be here for a long time. But actually, it always makes me laugh a little bit when I hear that introduction, and I'm introduced as the Simonyi Professor for the Public Understanding of Science, because I think that everyone expects that I must know the whole of science, and here I am to explain it to you all here in Liverpool. And certainly when I took over the job about 8 years ago, journalists certainly thought I seemed to know the whole of science, and I would get these journalists phoning up asking me to explain everything. I remember one time the Nobel Prize for Medicine had just been announced, and this journalist phoned me up and said, yeah, just announced for the discovery of telomeres. Could you tell me what a telomere is? I'm afraid to say biology is really not my strong point, but I'm a little bit embarrassed to admit that I was in fact in front of my laptop at the time, and I quickly pulled up the Wikipedia page to telomeres, quickly read what they were about, and then confidently told the journalist that yes, they're the piece at the end of the DNA which controls how long the thing will last, and then I realized, it's impossible that I should be expected to know it all. And I think, who was the last scientist that knew all the science that was available at that time? Perhaps Isaac Newton or Galileo, but since the explosion of knowledge from Isaac Newton, I think there's really nobody that individually knows it all. But it kind of got me thinking whether there might come a point where science might know it all. I mean, science, every time we open the newspapers, we seem to discover a new thing about our universe, a new innovation, a new piece of technology. I think people have great expectations that science might be able to tell us all the answers. So I was intrigued to see whether actually there are limitations to what science and mathematics can tell us about. And it set me off on this kind of 3-year journey that culminated in the writing of this new book, which came out this year, called What We Cannot Know, which tries to articulate whether there are any questions in science that, by their nature, we will never know the answer to. So in the book, I actually divided the book up into 7 regions of knowledge, which I want to sort of take you on a guided tour through the unknown during this presentation, a couple which I think are very particular to your own industry, because after all, that is what your own industry is about. It's trying to know about the future, the unknown. How much can you know about it? And I think that desire to know is incredibly basic in us. I think it's almost as basic as the desire to reproduce. It's driven our evolutionary survival, that desire to know what's going to happen next, for example. So actually, you start the book with a quote from Aristotle's Metaphysics. He starts the book with the statement, "Everyone by nature desires to know." But it's probably very dangerous at any point in history to say, well, we'll never know the answer to this, because who knows when the next kind of Einstein is going to come along and completely change your perspective on the universe. So I kept a few stories in mind of people who very confidently said, we're never going to know this. One of my favorite was Auguste Comte, who in 1835 very confidently declared, we shall never be able to study by any method the chemical composition of stars. And you might say, well, that's a very fair statement at the time, and we've still never visited a star and dug some of this stuff out. But what he hadn't taken into account is that, well, although we've never visited a star, of course, every night the star visits us. The light from the star comes down to Earth, and within a couple of decades, scientists had understood how to use that light to actually give us a very complete chemical description of what stars are made out of. So I kind of kept this in mind as a warning that to say that you can't know anything is very dangerous at any point in history. Of course, I'm not the first to kind of investigate the unknown. One of our great 21st century philosophers, Donald Rumsfeld, very famously talked about the unknown in this cryptic response that he made to questions about weapons of mass destruction. He declared, there are known knowns. There are the things that we know that we know. We also know that there are known unknowns. That is to say, there are some things we do not know. But there are also unknown unknowns. Those are the ones we don't know. And he actually got given the foot in the mouth award by the Plain English Speaking Society for this kind of response to the question from the journalist, which I think is actually a little bit unfair, because I think this is a wonderful description of different states of knowledge. The known knowns, I mean, that's partly my book is celebrating how we know what we do know, and the changes, what changes in history to give us a different perspective on our universe. And I think it's by celebrating the known knowns that we can go into the unknown. The unknown unknowns, well, they're very difficult because by their very nature, they're unknown. They're a little bit those black swan events, something that comes out of nowhere that you can't predict. They're the moments which really kind of change history. Taleb's book about black swans documents very nicely the different ways that the unknown unknowns can completely change a situation. But it's very difficult to take those into account because they're unknown. So I'm after these known unknowns. What are the things that you can know that you can't know, and how do you deal with those unknowns? And I'm especially after those unknowns which will always remain unknowable. Are there any? Maybe science can know it all. Another actually inspiration for this journey into the unknown was actually the person I took over this job from in Oxford. So my predecessor as the Simonyi Chair for the Public Understanding of Science was a certain Richard Dawkins. Now, Richard spent a lot of the later years, the tenure of his professorship, not talking about evolutionary biology and science, but talking about religion. His book, The God Delusion, sort of got him into a lot of feisty arguments with theologians. So I kind of braced myself for the questions that I would get from journalists as I took over from this, the ultimate militant atheist, what my own religious beliefs were. So I actually prepared an answer for them because I wanted to put a little bit of distance between religion and the science debate. So I actually told the journalists I actually was a very deeply religious man, and they were a little bit surprised coming from a scientist, mathematician, but I then went on quickly to say that my religion is the Arsenal Football Club. And every Saturday I go to my temple, the Emirates, formerly Highbury Stadium. I worship my idols. Each season I reassert my faith that this will be the season we win the Premiership, and every season my faith seems to be tested at the moment. But are there any Spurs fans here? Oh my gosh, Spurs fan on the sofa here, right? We're going to have a feisty question and answer afterwards. Well, I must say, at least we have a very good saint, because St. Totteringham always ensures that we end up above Spurs by the end of the season. Now, St. Totteringham had
all going so well.
St. Totteringham had a late appearance this season, I must admit, but last day of the season.
Unbeaten.
But so some journalists were happy with this, but others kind of pushed me. And I remember one debate on Northern Ireland radio on a Sunday morning. It was a philosophy and religion program, and religion isn't too far from people's minds in Northern Ireland on a Sunday morning. And I talked to the journalists beforehand, and I agreed, well, I'm happy to talk about the philosophy of science, but I don't want to talk about religion. And say, that's fine, that's fine. As soon as the little light went red, he turned to me and said, "Sir Marcus, do you believe in God?" Oh, sorry, that was a dreadful. I apologise to people from Northern Ireland. I won't do any more accents. And so we got into this really feisty argument about the existence of God. And actually, as a mathematician, I spend a lot of time proving the existence of things, or proving things can't exist. If you remember, Fermat's last theorem is all about the non-existence of solutions to equations. There do not exist solutions to these. But as a mathematician, I need a very clear definition of what it is that I'm trying to prove exists or not. So I kind of pushed the journalist and said, okay, well, look, if I'm going to engage in this as a mathematician, you've got to give me a very clear definition of what you mean by God. And he said, well, but God is something which transcends definition. It's beyond the understanding of the human mind. And I thought, well, that's a little unfair. You kind of played me out of the game by defining it as something that we can't understand. But actually, when I went away from the radio station, I thought, well, that's quite interesting as a definition, that it's the things that we cannot know, that it's the things which always transcend understanding. And of course, traditionally that's always been a kind of placeholder for the uncertain, the unknown. People will call it an act of God if they don't understand where it came from. And actually, there's this term, the God of the gaps, which was a derogatory term introduced by theologians saying, no, well, science seemed to be creeping, knowing more and more and more. Perhaps there was no room for this God. And they said, no, you should know God or something. But in a way, this book is also trying to reclaim that idea of the God of the gaps as a kind of like a positive idea and explore, if there are things that we really cannot know, what interaction do they have on a sort of theological basis? And I'm actually not the only one to talk about that idea. I did a debate with the chief rabbi a few years ago in Jewish Book Week. He wrote this wonderful book about science and religion, the Great Partnership, celebrating how actually we're after the same big questions in a way. And in preparation for that, I talked to a philosopher friend of mine at New College, and he's referred me to this theologian in Oxford. He's dead now, but he's a Marxist theologian, which I thought was quite cool, actually. I don't know how you do that. But so Herbert McCabe, and he has some very strange essays about Christian liturgy, but there was one in particular which had the following statement in it. It said, to assert the existence of God is to claim that there is an unanswered question about the universe. And actually, he goes on to say that religion really committed iconoclasm by giving this quite abstract idea far too many properties it should never have had. And of course, that's kind of what we get told as kids, and we reject very quickly when we engage in a kind of rational scientific view of the universe. But maybe there's still something there which is kind of the unknown, which is still can be part of a rational scientific approach to the universe. So I sort of kept that in mind as well as a kind of part of my journey. So the 7 edges of knowledge. Well, actually, the first edge that I explore, I think, is very relevant to your own industry and to so many people's lives, because I think we spend a lot of time as human beings thinking about the future. In fact, I think it almost defines our quality of consciousness that differentiates us from other species, that we spend a lot of time trying to map ourselves into the future. I made a program with Horizon on the BBC about consciousness, and we did this experiment. It didn't get into the program, actually, but it was an experiment that we did at California University. And basically, I had this beeper just went off randomly, and I had to write down what I was thinking about at that moment. And 80% of the time, I was thinking about planning into the future, trying to work out what was going to happen next. So I think as a species, we really just spend a lot of time, because it's given us the power to help to make predictions if we can help to navigate the present, if we can know about the future. And I think your industry is particularly involved in trying to make the best decisions about where to go next with incomplete information. Actually, I took with me on my journey an object. So each edge is accompanied by a particular object. And I think the ultimate symbol of the unknowable, of the challenge of predicting the future, is actually the casino dice. So I took this dice as a kind of a thing to journey to the edges of knowledge. And it really does the interesting thing about a dice is that I seem to be unable to predict as I throw it to the floor. That time it landed on a 2, but this wouldn't be interesting if I could predict it. But hold on here. My subject of mathematics is all about, when I tell people I'm a mathematician, I think they don't really know what I do in my office all day in Oxford, and I think most people think I'm doing long division to a lot of decimal places, and surely I've been put out of a job by a computer by now, but I'm sure many of you will have, at parties, sort of suffered this, like, I'm a mathematician, I'm an actuary, or the kind of look of horror that appears. But I try to, I'm very persistent when they kind of try and flee to the other end of the party, and I chase after them, and I say, actually, no, mathematics, at its heart, is all about pattern searching. It's about trying to understand the patterns in the data that has gone before to try and find that pattern to be able to read it into the future. And it is really our best tool, I think, for trying to predict what's going to happen next, because that is all about spotting patterns and trying to see where it's going to go next. Now, after all, we've understood the laws which control this dice as it falls from my hands. And, mathematics really should be able to predict what this is going to do. In fact, this dice, I have a very personal relationship with it. This dice, I went to Vegas and I thought, surely I can use my mathematics to cash in here and make some predictions about what this is going to do. It's just a bit of kind of Newtonian dynamics and things. Unfortunately, I lost a huge amount of money, but they let me keep the dice that we played with. So this is the dice that I brought back from Vegas. So it has a kind of very personal relationship with it. And I suppose the person who gave us this kind of belief that maybe we can know the future before it becomes the present is, wrong way, let's go that way, is Isaac Newton. Because Isaac Newton came up with the laws of motion, which absolutely describe the way this thing is going to fall from my hand, what happens when it impacts the floor and rolls. He invented the calculus along with Leibniz, which allows us to understand a world in flux, a changing world. And those tools gave scientists post-Newton the feeling that we really should be able to know. If we have more data, if we have complete data, the Newtonian physics says you can know exactly what's going to happen next, that it's a deterministic universe, that a complete description of now, the laws, you just go take those into the future and you'll know what's going to happen next. Even if that is true, and I'll challenge that in a little bit, even if that is true, if Newton is my hero in this story, I guess this guy here is the nemesis of this story. This is Henri Poincaré, who at the beginning of the 20th century understood that even if you have the complete description of the laws which control a dynamic system, and you know exactly how the thing is set up, even a little error in that can cause a huge difference in your predictions. And this is the idea of chaos theory. And chaos theory has really messed with many of our kind of attempts to be able to try and model and predict and know what's going to happen in the future. My favorite example of chaos theory, and it's the idea that very simple systems can have very complicated behaviors, and such complicated behaviors that are very sensitive to very small changes that they can do something completely different. So this is actually my favorite example of sort of chaos in action. It's a very simple system. It's a pendulum. Now, pendulums are usually so predictable, we use them to keep track of time. But this is a slightly different pendulum. It's two metal pieces jointed together a little bit like a leg. So the geometry of this is very simple. We know the equations which will control how this thing will fall. That's also a little bit of gravity, not very complicated there. But trying to be able to predict the behavior of this thing is almost impossible. Oh my God, that was vicious. I'm going to try it again because I need to get out of the way. Whoa! Right, let me do that. It's hitting my... there we go. Whoa! I think even knowing when it's going to finish is almost tricky. But the real challenge here is, okay, that was crazy behavior, but can I repeat that behavior? So try and remember what it just did. I have a little notch here, which I try and use this to try and repeat the behavior as it goes down. So is it going to do anything like it did before? Oh, it's got kind of late. Well, it's hit me. Oh, dear. Right, let's... let me try that again. This is my favorite desktop toy, so I can play with this for absolutely hours. But so let me do one more go. So I think that's completely different behavior because it's sort of whizzing around quite a lot, anti-clockwise now. But so this is the challenge of chaos theory. You might have a complete description, but trying to repeat the behavior, this thing is so sensitive to small changes, it will do something completely different. And that's the challenge with whatever you're trying to do. Are you in a system which has actually got that unpredictability to it? One of my other favorite examples, another desktop toy I've got here actually, is this little pendulum, another pendulum, but it's got 6 magnets, and the pendulum is attracted to the magnets. In fact, I use this to make all my decisions in life because all the magnets have answers to questions on them. So you can ask a question. So it says no way, definitely, maybe, yes, ask a friend, try again. So well, let's ask it whether I should make a bet on Arsenal winning the Champions League this season. Let's see what it's going to say.
No, it's rigged.
You think it's rigged? No, it's very unpredictable. You try and predict what it's going to do. I've got a little example that we did in the lab. So this is actually just with 3 magnets. But you try and predict which magnets the pendulum is going to get attracted to. It seems completely crazy and random, but it's a completely deterministic system. This is not random at all. So it seemed like it was going to be the top one, but eventually it settles on the bottom one here. How's this going? What, should I make that bet?
It says ask a friend. If I'm
Ask a friend. OK, should I make the bet?
No.
All right. Yeah, there's a bit of bias there. You've got to also know who you're asking your expert information from. So I think... good. No, but here's an illustration of the sensitivity of this system, which again has very simple dynamics. I did 3 experiments where I started the pendulum off in the top left-hand corner. The first, so I colored the magnets yellow, blue, and red. And the first run, it whizzed around and eventually settled on the blue magnet. Actually, you can think of this a little bit like an asteroid flying around. The attraction is a bit like gravity. So, and the 3 planets, which planet is going to get wiped out? And actually, Poincaré discovered chaos theory because he was trying to do exactly that. He was trying to understand whether our solar system was stable or not, and then understood that it's so sensitive to small changes that it's very hard to predict whether our solar system is going to keep on doing things clockwork into the future or whether it's just going to fly apart. So the second experiment, I changed the 6th decimal place of one of the starting coordinates, And you can see, to begin with, it sort of followed a similar path, but very quickly diverged and took a completely different course and crashed on the little red planet. The third time I changed again the 6th decimal place, very small amount, ended up at the yellow planet. And this is a computer graphic which helps you to make predictions about what this thing is going to do next. And it's not like mathematics is completely useless. I mean, we've done amazing things with Newtonian physics. We've been able to recently land a spaceship the size of a washing machine on the side of a comet. That was because we had the power of predictability of what was going to happen into the future. So the way you read this picture is that if you start the pendulum over a yellow region, it means it's going to end up at the yellow magnet. So you can see there's a big swathe of yellow there. That's a very predictable region because it's just near the yellow magnet. The other magnets don't have the strength to pull it to their side. So there's a very predictable region. But it's interesting, there's another predictable region which is kind of on the other side of the yellow magnet, this big sort of yellow blob on the other side. This isn't sensitive to small changes. You can make a little bit of inaccurate measurement and still it'll stay within that yellow region. What it does is just swing backwards and forwards and ends up at the yellow magnet. The other two don't have the strength to pull it aside. But I started my pendulum off in the top left-hand corner. And this is an example of a geometric shape called a fractal. A fractal has the property that it has infinite complexity. As you zoom in on it, it never simplifies. It has infinite sort of complexity. So it might mean, you might hope that, okay, well, maybe I need to get a lot of data, but once I've got through to like 10th decimal place, then the region just becomes yellow, and I know now that I've got enough information to predict it. But this says, no, the 10th decimal place, you're still going to be seeing yellow, blue, and red. You say, well, I'll go a bit deeper, zoom in a bit more. And the quality of this area says you're never going to know what's going to happen because a small change in the next decimal place can still shift it from a yellow to a red to a blue region. So this is a region where you cannot know what's going to happen next. Now, this is a very simple system. You say, well, why does that apply to us here at this meeting? The point is that this kind of dynamics affects so many things that we want to kind of predict into the future. I mean, it affects climate, so climate from one day to the next is very unpredictable. There are regions in the climate which are very predictable, which is why I don't think you can use chaos theory as an argument against the belief that we're suffering climate change. But on a day-to-day level, I've been down to the Met Office and we've seen runs of trying to predict the weather into beyond about 5 days. They've got a huge amount of data coming in. They put that data into their models. They perturb the data a bit, so they know there are going to be a few errors. So within 5 days, there's a kind of predictability. But they know there's a moment when suddenly these predictions start to bifurcate, and you really can't know it's almost like a cutoff moment. From the 6th day onwards, the models just have an unpredictability about them. And so it's important with any dynamic system to know, are there regions where you can predict? With the weather, there are sometimes. If you're in the Sahara Desert, it's like sitting in that big yellow blob. Little changes aren't going to really do much to the weather there. But we live in that kind of fractal region where the weather is very unpredictable. But it affects things like trying to predict asteroids, for example, or the behavior of spaceships, population dynamics. But it also seems that it might be affecting something like the economy. Because the economy is just basically something with certain pushes and pulls in it. There's data being fed in. Surely we should be able to apply the tools of mathematics to something like the economy. And actually, as well as an object, I also took with me a person to the edge of this knowledge to try and explore how somebody dealing with these particular challenges copes with the unknown. And this is Bob May, who's a colleague of mine in Oxford. He's a mathematical biologist, and he understood how chaos theory is very important in understanding, for example, population dynamics, also sometimes in virus spread as well. There are moments when you have a high multiplication rate like measles that things can become very unpredictable. But he's now working, actually I should call him Lord May because he's a cross-party member of the House of Lords. And he's now working with Andrew Haldane at the Bank of England, trying to understand whether the crash of 2008, for example, was something that you could predict, or was it really just that the equations had gone into a region that now was very sensitive to small changes, and there was no way anybody could have made any predictions there. So I went and had lunch with him at the House of Lords to ask how he was getting on explaining to MPs a bit of mathematical chaos theory. And he said, it is important, he said. So not only in research, but in the everyday world of politics and economics, we'd be better off if more people realized that simple systems do not necessarily possess simple dynamic properties. So I asked him how he's getting on with these MPs, and he said, Marcus, they're mostly interested in their egos here, not in mathematics. But it's interesting. I think for an industry like yours, the power that you get from being able to predict is absolutely clear. But maybe the power that you get from knowing when you cannot predict, to be able to know when you've gone into a region which is fractal, which is chaotic, may be more powerful. Because that's the moment when you need to hunker down and be more conservative because you know that you cannot know. So I think that is it's powerful to understand in your own particular dynamical systems where are the tipping moments when you've gone into a region where you can't know. So I wondered, what about my dice? Is the reason I can't predict my dice because it's actually chaotic? Well, I got a little bit of a surprise because I discovered a bit of research done recently by some Polish mathematicians who did some kind of high-speed camera capture of the dice as it fell and hit the table. And this dice turns out to be more predictable than you might expect. But it depends where you're playing. Here are some kind of models. They're pictures rather similar to the pictures I made to help you predict that chaotic pendulum. So these are actually graphs which measure. So I've colored the faces of the dice yellow, blue, green, and I'm going to try and predict which side the dice is going to land on. What I'm varying here is the height above the table and the angle at which the dice is leaving my hand. And I'm varying these two things and seeing, is this incredibly sensitive? So a small change just means it's going to flip from one side to the other. The interesting picture is that one in the top left-hand corner, because this is not fractal. It's got very clear regions of predictability. A small change doesn't cause it to flip from the yellow to the blue region only on sort of one border. This is the craps table you want to look for. So if you take one thing away from my talk, it's the following. Okay, so when you're in Vegas, look for a very soggy craps table, a really old casino, it's a bit down on its heels, because you want the craps table which has kind of a bit of a soft surface, because you want the dice to lose energy quite quickly, and then it's described by the dynamics in the top left-hand corner. So for example, this sofa is quite squidgy. Okay, so the idea, what they discovered is that if you let the dice fall onto a squidgy table, it's more likely to land on the face, which is down on your hand. Okay, so I've got 6 down on my hand, so we're going to let the dice fall. Oh, it's gone on the. Oh, it's 4, but that's good. Let's try and see if I can keep it on the. It actually looks quite bouncy, this table. So that's the trouble with trying to make predictions. So actually, I put that on the. Yeah, doesn't work. Never mind. That's why I like maths. You can be really sure about the future. But maybe that's an indication that the thing has started to move, actually, because each time I did that, it was doing completely different things, a bit like the dynamics of my pendulums. Maybe it's an indication that this table, it was bouncing quite a lot. It wasn't losing energy. It's gone into this region, which is much more fractal. So a very small change means that I can't make a prediction about what's going to happen next. So I think this is, those MPs may not be sort of exploring the importance of chaotic dynamic systems, but I think an industry like yours, it might be important to know those moments which it's going to actually tip into something you cannot know, or where you can be confident of your predictions. Of course, actually, all of this was under very classical 19th century physics, where we believe that things follow laws and it's very predictable. So I'm going to take you a little bit into some unknowns, which you may think, well, why does that? What's that got to do with my industry? But actually, I think it's a way of thinking which I hope might change the attitude towards your own particular questions. That's important that you might learn from other regions of unknowability. So actually, in the 20th century, we realized that the deterministic physics of Newton may not be the physics which controls the universe. Maybe the physics which controls the universe actually has at its heart unpredictability, randomness. And this is the edge of quantum physics. Quantum physics, I'm going to, I said I would really test your audience, so I hope your heads are clear, because we're going to take a little bit of a tour into the unknown of quantum physics, because quantum physics has at its heart the idea that maybe there are things that, by their nature, you can never know. And actually, the object I took with me on my journey to the edge of the quantum was this pot of uranium that I bought on the internet. It's amazing what you can buy on the internet. And it's interesting, so I actually bought it on Amazon, and you know you can write little reviews on Amazon. So I was quite intrigued by some of the reviews. So here was one who said, "So glad I don't have to buy this from Libyans at the Mall anymore," which I thought was quite sweet. There was another one which was complaining. He said, "I've had this for 4 billion years, and it's half full now." Oh, you're a good audience. They get the half-life joke. They're a smart lot. Good, so you're going to be ready for this, because I think one of the challenges, and actually the pot of uranium tells me the rate of radiation that's being emitted by this little bit of uranium. Oh, I probably shouldn't do that. Oops. No, don't worry, it's not weapons-grade uranium. Oh! Sorry. So actually, on the side, it says that this thing is emitting 984 counts of radiation per minute. So we have a kind of average assessment of how much it's radiating. But what this can't tell me, the details inside here, and actually what physics cannot tell us, is when it's going to radiate. We know over a minute, on average, there'll be 984 bits kicked off this uranium. But there seems to be no mechanism in physics or science to say when that's going to happen. What's the moment that it's going to happen? It seems to be completely and maybe genuinely random. And actually, at its heart is a theorem that this guy came up with, Heisenberg. Some of you may have heard of this thing, Heisenberg's uncertainty principle. And Heisenberg's uncertainty principle says that actually you can never get complete knowledge about a system. And maybe that's an interesting message, not just for the quantum, but for the universe and our interaction with it more generally. So he said, for example, in Newtonian physics, if I want to describe an electron, I need to know its position and its momentum, how it's moving, and then I can make predictions about what it's going to do next. Heisenberg says, actually, you can never know both of those things. The more information that you get about one particular system, so for example, the position, you get an uncertainty in the range of possible values for the momentum. That suddenly becomes an unknown. You might say, well, I know where it is now, so I'm now going to measure its momentum. But as you measure its momentum, and you get more and more detail about that, the way it's moving, you lose information about the position. Suddenly the position, it could be anywhere. And it's not a fuzzy kind of principle, it's a very precise mathematical formula. So this is what I've written on Heisenberg's blazer here, is this is the uncertainty in the position. So as the uncertainty decreases, I know more and more about the position, the delta x. In order to make this equation true, I have to make the momentum, the uncertainty in the momentum get larger. So I know less and less about that. And as you pin down the momentum, the uncertainty in the position goes up. So this is at the heart of the way we must do physics. Actually, if you indulge me, my favorite physics joke is about Heisenberg. So Heisenberg is bombing down the motorway in his BMW, and he gets pulled over by the police. The policeman gets him out of the car and says, "Sir, do you know how fast you were going?" And Heisenberg goes, "No, but I know exactly where I was." That's good. So anyone, you shouldn't have to explain a joke, but anyone who's going, I don't see why that was funny. It wasn't really very funny. But the point is that because he knew his position very well, it meant a great uncertainty in the different values that his speed could have been. So here's a follow-up for those who want to laugh on the next one. So the police officer tells Heisenberg, "Well, you were going 200 kilometers an hour." And Heisenberg goes, "Oh, now we're lost." Yeah, good. A few more laughs there. Excellent. During the question time, I'll fill it. There's even a third one, because it turns out Schrödinger is in the back of the car. But you can ask me that during the question. Actually, we've moved on, and we believe now that maybe the language is wrong. And this is an important thing in transformations in scientific knowledge, and maybe very relevant, is your use of language. And we now understand that maybe it's wrong to say that that electron even has a momentum, an electron that we're trying to know. That actually, before we observe it, the electron doesn't have a fixed position, that it actually is spread out across the universe, that you might have heard this thing, the electron is sort of in two places at the same time. And we have now a description of the electron, not as a position, but as a probabilistic wave function. So it tells you the probability that you might find the electron here as opposed to here. But the electron doesn't have a position until you observe it. So, for example, this wave here describing the electron, the height of the electron, the wave says, well, I'm very likely to find it here. When it's low, it says you're very unlikely to find it here. But the crazy thing about this is that physics now says, even if you run the experiment the same every time, you can get a different answer each time you observe it, because it's just a random roll of the dice which decides which place it's going to be. And this really goes against the heart. Many mathematicians have this feeling that we should be in a deterministic universe. You set up the universe like this, run the equations, you get the same answer each time. If you do 2 times 2, you're not going to get a different answer to 4. This kind of says, well, actually, the way the universe works, maybe that isn't true, that each time you run the thing, you're going to get a different answer out each time, which is a very sort of threatening idea. And surely, is that really how the universe works? Surely there must be some mechanism which is telling me when this thing is kicking off some radiation. And I'm a believer that this is just an interim stage in our understanding of the unknown, that we will come up with new ideas which help us to know when that thing is going to radiate. And I'm not the only one. Einstein, too, really was very mistrustful of this kind of probabilistic view of the universe. He wrote, "Quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice." So I think that's interesting in any system. Is there a genuine randomness inside here, or are there hidden mechanics which are controlling this thing? Well, I've given you 2 edges, or another 5 edges. I want to give you time for some questions to ask me, but I will quickly whiz through and tell you what I think are some of the other unknowns that we may never know about. What my uranium is made out of. We used to think atoms were indivisible, and then we discovered, we used to think things were made out of earth, wind, fire, and water. And then we discovered, no, there are atoms in the periodic table. We thought these are the building blocks. Then we realized, no, these can be pulled apart into electrons, protons, and neutrons. We thought those were the indivisible things, until the protons and neutrons came apart into quarks. We now think that's the last layer, but how do we know they may not come apart in the next generation when we have a new view? In fact, we have this idea of string theory. Maybe actually these are just little vibrating strings at their heart. So maybe digging down and knowing when we've hit the last layer is a genuine unknown that you can never know, that may not pull apart into yet again something else. So the very small, I think, gives you a challenge of the unknown. The very big as well, whether the universe is infinite. Our view of the universe has completely transformed each generation. We thought we were at the heart of it all, the sun, the earth at the center of it all. And then we realized, no, actually there's a sun and we're going around, the planets are going around there. But then we had to pull out again. We realized that our sun was just one of many stars, and we have our Milky Way, which also turns out not to be unique. There's many galaxies out there. So each generation, and I've gone through another shift where we now think there are multiverses, other universes. But actually, we have a bubble around us from which we can get no information. There's a kind of cosmic horizon beyond which we cannot see, because information travels at the speed of light. The universe has been going for 13.8 billion years. That means there actually is a horizon beyond which we cannot know anything. So we now actually believe we may not be just one universe, but many universes. But could we ever know that? So that's the challenge of the very big. Time. Well, my time's running out. We've got 5 minutes left, and I want to leave some time for questions. So turns out time might have an end, but did it have a beginning, or what happened before the Big Bang? What's happening inside your heads at the moment? Consciousness, I think, is one of the great hard problems. Maybe, are you a bunch of zombies with no conscious experience? I mean, some of you are looking a bit zombified this morning. God, quantum physics on a Friday morning. But we have this kind of challenge of the hard problem of consciousness. We all have this thing we call consciousness inside our heads, but as Wittgenstein said, it's a bit like a box. Inside it, we don't know what's happening in anybody else's boxes, but we all call it a beetle. But is your beetle anything like mine? Is your consciousness anything like mine? And the real challenge, could my iPhone ever become conscious? I assume you're all a bit like me and have a consciousness, but when will this say, iPhone think, therefore iPhone am? And, well, that's quite good. I should sell that to Apple. And actually, the last edge is the edge at the heart of my own subject, which says even mathematics, We can prove that there are things about numbers which are true, which we can never prove are true. So we actually have the tools to turn on ourselves and to show that there are things that we cannot know. So I think I'll give some time for since my time is running out, the end of the universe is nigh. So thank you very much for your attention.
Well, thank